So taking a look at differential equations is basically we're trying to do some integration here, but we usually have some more information about the problem, makes it into an equation where we've got to integrate to solve. Just to jog your memory then, some things we've been talking about, like if you have y prime, that's the same thing as dy dx. We've been using these different notations, and it's going to make sense why we like the Leibniz notation better when we do this. So to show you what I mean by we need to solve some equations that they give us, this first one here I'm going to rewrite with this notation, and then I'll just let you have a look-see at what I'm going to do to solve this. So the first thing that I'm going to do is, do you remember what well, we talked about the bottom of this fraction a lot. Do you remember what the bottom of that fraction was supposed to mean when you read it? With respect to x. So basically I'm going to shuffle my variables so they match the side of the equation that it's on. So what I mean is I'm going to move this to be y dy equals 2x dx. And that way I've got one side of the equation with respect to y and the other side with respect to x. And now to figure out what the equation used to be, because see, this is the rate of change in y is given by some function. We want to reconstruct the function. That means all I got to do is integrate both sides. So when I do this, I'm going to have y squared over 2 equals x squared plus a constant. And you probably want to do some more solving on this. You know, like we could call this y squared is 2x squared plus a constant. Notice that the constant just gets to stay a constant because 2 times a constant is still a constant. So we don't have to worry about that. We could probably leave it like this. Some of you might be tempted, and it would be fine to call this the plus or minus square root if you wanted it explicitly. Okay. So I'll have you try this next one. See if you can solve this differential equation by separating your variables and then integrating. Okay, so judging by the silence, you're either just bored out of your tree or you're already got an answer, or both. So I'll try to catch up to you here. I'm going to move the 1 plus y underneath, and then I'll move the dx up. So now my equation is separated in terms of the variables that they represent, and I can integrate both sides. So here I'm going to have natural log of 1 plus y, and that's going to be equal to x squared over 2 plus a constant. And I can still do better than this. How could I separate that natural, like how could I get y all by itself? Any ideas? Yeah, we could rewrite it as an exponential. So that's log in base e, so it would be e to the x squared over 2 and some constant is equal to 1 plus y. And notice I don't need the absolute value anymore because that exponential is always positive, so it can magically disappear. So if I rearrange some things, then I'd have y equals e to the x squared over 2 plus a constant and subtract 1. So that would be the equation we started with. Now we're going to talk more about this specific one. So before we get more specific on it, one thing I'll need to alert you to, I suppose, is this thing that says a rate of change is proportional. So when you basically hear these magic words, it's not always explicit to you, but I guess I'll... Sorry. One more time. There we go. When you see that rate of change is proportional, this is going to be continuous growth. It's going to be this exponential growth that we're working on. I'll show you how you get it, but it's like when we did exponential growth in your Math 12 class. So this would be y equals some constant e to the kt, something like this. Does that look familiar from Math 12? There probably wasn't as many letters in it, right? But Okay, so I'll show you where it comes from, and then we'll practice it. Maybe it'll sound more familiar, but we have done stuff like this in Math 12 when we talked about things like, you know, a colony of ants doubles every 2 weeks or something like that. This time we're going to take a look at what happens if your rate of change is proportional to your population. And this is basically like, if you're going to go on to the natural sciences, this is like huge, because you think about something like, how does a population grow? Well, it's proportional to the amount of people usually, because people reproduce, and that comes from the amount of people in your population. More people means the rate of change is bigger. Less people means the rate of change is smaller. Or things like, you know, how fast a rumor spreads. Generally, it mushrooms, right? Like a viral video or anything like that on YouTube. More people that know about it, the more it keeps spiraling and spiraling, right? So what you have is, say, for example, you had 100 people, and 10%, let's just say this is like a secret that's getting shared, right? You're not supposed to tell, but you know someone's going to tell, right? So 10% of the people end up saying it. Now 110 people know your secret. And then again, if you assume that psychology is fairly uniform, I don't know if that's a good assumption or not, but if you assume, okay, well, 10% more are going to, just like they did before, 10% of those people are now going to, you know, spread this secret around. Now there's 121, and it keeps, you know, mushrooming that way. So this is the equation that you're trying to model, is that you're saying the rate of change is equal to some constant times whatever my population is now. In my example, that's 10%, and the population was 100 people. So if we want to total everything up, we'd have to do this differential equation, and here's what we'll get. dy over y equals k dx. And it looks very similar to the last one that we worked out. This will be, when I integrate, natural log of y equals kx plus some constant. And then I'll rewrite it. So e to the kx plus some constant is equal to y. And using your exponent laws, what I could do is e to the kx plus c, that could be like this. So same base, I would just add those exponents together. So hopefully that's legitimate. People follow that. And e to the c, that's a constant to a constant. It's just another constant, right? It's just some number here. This is just some constant as well. So we can simplify it out to look like this. And that's how you get that formula for proportional growth. You can't really derive it without calculus, because you'd need to know how to, you know, model this equation and do integration for it. So let's try and solve a problem where they've given us some information about its population and its rate of change. So the first thing you got to get used to hearing is well, I can't think of a time when they've ever said, this is exponential growth. They don't just throw it out there to you, but they tell you that the rate is proportional. So basically, when you hear that the rate is proportional, you know you'd be solving this differential equation. Here it is again. That's what we're going to kind of clue into, that we're going to have to do this process. But we know what the end result is. This here is the end result. So you don't need to do the integration if you recognize it. You can say, okay, it must fit into this. And here's the information I have. So at time 0, y equals 2. This is, you know, 0 is friendly, it's your favorite, because when you stick in 0, good things happen, things simplify out. So that's what I would like to do here, is that'll be the first piece of information that I use, is time 0, and watch what happens. So, actually I know that y equals 2 there, so I'm going to just write it down as 2. So can anybody simplify this one more step further? Yeah, it's just c, because that becomes a 0, which means this whole thing becomes a 1. So the constant in this case is 2. So I'm able to find my constant right away, which was handy. I now have a model that looks like this. I don't know what k is, but you're going to get more information in your problem, and that can help us find k. So in this case, I'm going to substitute it in, and I'm going to have 4 equals 2e to the k, and it's at time 2. So if I do some solving here, I'll get 2 equals e to the 2k. How could I solve that? Natural log. It's base e, so that means I'm going to need to use natural log to get this exponent out. So natural log of 2 is equal to 2k. So k is equal to natural log 2 divided by 2. Okay, so I end up with a constant here, k, of about 0.347, something like that, to 3 decimal places. And if we were talking about continuous growth, and we were actually told that this grows at, is that not the right number? Is that okay? Okay. If we were told it grows at 34.7%, that's how we would use that information, is this is like our growth rate for continuous growth. So this would be 34.7% if we were growing continuously. So we put this into our model now. We have a complete model that we can use. 0.347x. And now it wants to know what happens when the time is 3. So all we have to do now that we have a model is substitute it in for 3. So y is going to be 2 e to the 0.347 times 3. And try and keep as much accuracy as you can in your calculator. The more rounding you do, for example, if you use 0.347 instead of the number that's looking at you in the calculator, you've rounded it, and it might seem insignificant to you, but remember, this is an exponential graph. I believe that there's some fact, like if you were actually chart an exponential graph and use regular grid paper, I think it's like by the time you go a meter along the x-axis, you've already hit the moon or the sun. It's like because it grows so fast vertically, those little itty-bitty moves that you think you're just rounding could actually introduce significant error. So don't round when you do this. Make sure you keep the numbers in. Okay, so now I've got, so it looks like we get 8.485. So that would, there's no context to this problem, but I'm assuming it's some sort of population or maybe a weight, something. So we'll put some context around it now, and we'll see if we can solve the problem. It's identical to what we were just talking about, is we're trying to build a model from the information that we have. And this time we need to talk a little bit about the context of what a half-life means. So physics people, can you explain what a half-life is?
The time you need for certain element to decay into half of its original volume.
Right. So in this case, if this plutonium takes 24,360 years to decay, that means if you started with 10 grams, it will take 24,360 years to get to 5. So that's why people usually get scared of nuclear energy, because when things go wrong, they go wrong for a really long, long time, because that whatever's in the atmosphere polluting won't be gone for many, many, many years. But anyways, that's another topic. So it says we've got 10 grams of plutonium. Actually, I would kind of like to know if that's, you know, how factual that is. I don't know how bad the disaster was in for the amount of plutonium, but it seems like very insignificant that 10 grams would have caused all those troubles in Chernobyl. How long will it take for there to be only 1 gram? So 1/10 of the nuclear pollution that they started with at that accident. So what points, this is all the information we know, what points could we use to help model this problem? Yeah, 0, 10 is a good one. So 0, we have 10 grams. What else could we use to model the problem? 5. Yeah, so 24,360 and 5, so. Oops, sorry, they're backwards there. 24,360, and there's 5 grams. Okay, so now we'll create the model for this, and then we'll use the model to try to solve for when there's only 1 gram of plutonium. So at this point, I'm going to let you guys give it a shot, see if you can model it, and come up with a working model. So I'll try to catch up to you. Okay, so it's quite small this time. So I'll write it down as negative 2.8, what do we have here? 45 times 10 to the negative 5. It is quite small, and it's negative, so let's put some context behind it so you can think about, why do you think it's negative? Yeah, it's decreasing. If it was positive, it would be getting bigger, but this is decreasing, so it's a negative number. Now, why do you think it's so small? Is that an error, maybe? Should we be worried about how small it is? No. Okay, how come? Not worried, just don't know.
The period of years is really long.
Yeah, it's a long time. 24,360 years. That's like, you know, your great, 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 and on kids will be, you know, you'll be long gone by then. They'll be around, and that's just one period of the half-life. Okay, so now I've got my pieces. I'm going to use the model to try and figure out when there's 1 gram left. So my model is this. And I might as well put it in here as the natural log 1/2 divided by 24,360t. So that's my model. And I want to know when that equals to 1. So what I'm going to do, of course, is the smart thing and use the calculator. It's possible that you try and solve this algebraically, but realistically, you're going to have to use a calculator to get a number out of this. So we might as well just let the calculator do the work here. We'll put it in as, where's my natural log? 1/2 divided by 24,360. And that whole thing is times by my x. Okay. Now, if you're thinking about the window, it's huge because it's gone from, it's 24,000 years in every half-life. So what I'm going to do is I'm going to probably make this like, I don't know, 100,000. That'll be like, how many will be that? 4 half-lives. So that means if you're trying to just get a rough estimate, 1 is a half, 2 is a quarter, 3 is an eighth, and 4 is a 16th. So I should have far enough. This should be far enough, but anyways, and of course it's backwards. That should be 0, and this one should be 100,000. And then the scale on this thing, I'm just going to use about what the half-life was. You know, I don't want to see all those tick marks. And it's never going to go below 0, and it starts with 10 grams. I might as well keep it like that. So hopefully this is a decent picture. Yeah, so it looks pretty good. I want to know when it equals to 1, so I'll go and put 1 on this graph as well. And then I'll find where that they meet. So it's somewhere over here. Like I said, somewhere between 3 and 4 for the half-life. Let's find this intersection. Okay, so I'll guess right about there. You could use the zero method too, by the way, but this will work. 80,922.168 years. So a long time. Maybe they would accept an answer of a long time. Okay. I guess I'll have to zoom out of this a little bit. Okay. So a manufacturing plant notices sales drop from 100,000 to 80,000. If sales follow an exponential decline, what will they be after 2 months? So you definitely don't want to be in a business where you just lost 20% of your business in 1 month. That's a scary, scary situation. But we'll pretend that's practical, and we'll see what do you think that they're estimating their sales to be at if this continues after 2 months. So see if you can model it. See if you can come up with the estimate in your model. Okay, so the 2 points you can get from the information, at time 0, you've got 100,000, and then in the first month, you go to 80,000. So in the next month after that, if you find your constant is natural log 0.8, the next month you're going to end up at 64,000 sales after that. Okay, so I hope you're getting sort of the hang of how to do the exponential model. Let's talk about when it's not quite as straightforward. We'll find some strategies to make it a little more straightforward. So this one is, we have these fruit flies that grow exponentially. If there was 100 of them on the first day, 300 of them on the, 100 on the second day, and 300 after the fourth, how many were in the original population? So we're trying to go backwards here. So what you could do is you could make points like this. Oops, sorry. Sure, we'll call it that. And then, so this one would be time 4. There'd be 300. You could do this, but then it's going to be harder to find your information because you don't have that magical 0 that you really wish you did. So how can we get a magical 0? I've got a hint here for you. What do you think of this? Yeah, if you think of your graphs, what kind of transformation has happened if I go t minus 2 instead of just t? It goes to the right 2. Yeah, so basically that would be saying then when we stick in, if I change my model now and pretend time 0, there was 100, and at time 2, there was 300. That's one way I could approach this problem. What will there be in the original population? I'm looking for -2. Right, you can adjust your graph. You can kind of think about the way you could shift it, and then you have this nice 0 you had before. It's possible to do without that shift. However, the algebra is a little bit more involved. So that's my recommendation is if you don't have the initial population, pretend you did, and then back up. Right? The model's still going to work. It basically will look like this if you think of the picture. Here's my picture, and actually these fruit flies are growing, so it's going this way. So all you're doing is shifting it over so that you can deal with, instead of day 2, you're dealing with day 0. So you just moved your graph over to compensate. Okay, so we have 100 is going to be my constant, and I'm looking at 300 is 100 e to the k times 2. And now I'm on day 4, but from my frame of reference it's only 2 days past. So this will be 3 is equal to e to the 2k. So 2k's are equal to the natural log of 3, and k is the natural log of 3 divided by 2. So my model will be y equals 100 e to the natural log 3 divided by 2 times the time. So by doing that shift, it's still a simple problem. You just have to think in your mind that that would be the easiest way so I can get that 0 back. And now remember, we're not finding the initial population at time 0. We're finding the population at -2 now. Because relative to where I'm starting, if 0 is on day 2, then -2 will be at 0. So this will be 100 e to the natural log 3 divided by 2. Times -2, and let's just see where we're at then. We have 100. We should expect the number to be smaller, otherwise we've made a mistake somewhere, but because the population's growing and we're going back in time. So yeah, so I have 33 1/3 fruit flies, so I guess 33 if we had to round to the nearest fly. So my advice to you is you should always try to keep time at 0, because that is such a convenient point for making up this model. So if you don't have time 0 in the problem, shift one of the points so that way you do have time equal to 0. Okay. Now this, do you guys do Newton's law of cooling in physics? No, you do thermodynamics? No? Okay. Anyways, Newton's law of cooling is one of the things that obeys this law. So you can go home and get your thermometer out of the cupboard, boil a cup of water and time yourself, and then try and race to see if you can fit. No? You got better things to do, right? Anyway, thought I'd try. It does actually work. I've tried this before in classes. I am that big of a geek that I've actually tried this. So this is the situation. A room is 60 degrees, and a cup of coffee with temperature 100 degrees is placed in the room. Newton's law of cooling says that they will change with an exponential decay model. The other way you might hear that is, the change in temperature is proportional to the current temperature. And if the coffee takes 10 minutes to cool to 90 degrees, how long will it take before it's 80 degrees? So there's a little difference here in terms of what we're talking about in the problem, because 60 degrees is the room temperature. So hopefully you have the logical thinking skills that will tell you that this cup will never go below 60 because the room would heat it up, right? So there's an asymptote on this graph. I'm going to try and build up with you some of the ways that you can common sense your way through this problem, and then I'll show you the actual calculus for it. But the common sense road, if you really want to try and understand what I'm saying, because it's much simpler, but you truly have to understand the problem. I think about it this way. It's not unique to Newton's cooling law. It's also, population animals, so it could be taken in a different context. But basically, if we're trying to match it up, all of my exponential graphs have some form like this, right? Sorry, we had something like that. Do you know why we didn't have to deal with this before? The reason we didn't have to deal with this before was, I guess eventually you go far back enough in time, you'll have no fruit flies. You let the plutonium decay long enough, you have no plutonium. Of course, theoretically, it'll never hit 0, right? But that's the asymptote. And when the asymptote was 0, we don't add plus 0, because we're not crazy, right? We're just a little eccentric about math. So in this case, we know the asymptote is 60 degrees. It can never fall below 60 degrees. So that's what I can put into my problem then when I update my model. Okay. Now, the temperature starts at 100 degrees. How many degrees will decay in the cup?
40.
What do you think?
100 to 60.
Yeah. Just give them a chance. You were correct. Just give people a chance to think about it. How many degrees are going to decay in this cup? It's 40, yeah. Those of you who've been saying it out there, you got it. It is 40 because you have 100 degrees. You'll never go below 60, so how much do you lose? You would lose the 40. So that's this number right in here. That's what's going to be decayed. Here's what does all the decay on that number. That graph, the exponential, will wither away that 40 degrees. So coming up with my model then, I can update it a little further. 40 degrees here will be my initial amount because I started with 100 and I'll never go below 60. So that leaves me with only one unknown in my problem. If I could common sense my way through it like that, now all I have to do is use one data point to figure this out. It's not helpful to use times 0, you have 100 degrees, because you'll just get back what we have here. So watch, if I go 100 equals 40 e to the 0 plus 60, and you go, yeah, it's right. But it didn't tell us anything new about the problem. So you already thought your way through what the initial problem was because we said you're going to decay 40 degrees at the very beginning of the problem. So that point's not helpful to us anymore. But we do need one more point, and we have one more point. It's right here. 10 minutes to get to 90 degrees. So that's the one that'll solve the rest of the model for us. 90 is 40 e to the k times 10 plus 60. So again, I'm going to keep telling you what's happening so you try to put some context on this problem because it makes life a lot easier. If you think about it, this is now going to be 30 is equal to 40 e to the k times 10. Because if I wanted to go from 100 to 90, now there's only 30 degrees left to decay. So I'm saying you started with 40 and it's going to keep decaying until you hit 30. That's the temperature is 90 degrees. So we'd have 3/4 is e to the 10k. So the natural log of 3/4 is 10 k's. So k is natural log 3/4 over 10. And now I have a model that will model this cup of coffee. So we have 40 e to the natural log So here's my model, and now I want to know when will this hit 80 degrees. So again, this is going to be a calculator exercise. We're going to have the calculator do the hard work for us. We'll go in and put the model in the calculator. So 40, my exponential graph, and I've got natural log 3/4, and I divide it by 10, and then multiply by x. Don't forget that you have to add the 60 because that's the room temperature. And I'm interested in knowing when this graph is going to hit 80 degrees. So I will go and I'll think about a decent window here. It took 10 minutes to drop 10 degrees, so I'm going to guess it's probably safe if I did 15 minutes. So that'll be a total of 25. I think that'll get me there. And then the coffee cup, the asymptote's at 60, so you got to be above 60. So I guess we might as well start there. And I'm interested at 80, so whatever. I guess I'll start at the full 100 degrees so you can see a picture of it. And where on earth did it go? Okay, apparently I didn't put it in right. Let me double check my 40 e to the natural log 3/10 times x plus, oh, sorry, that's probably, I don't know if that will actually make a big difference, but plus 60 there, okay. And then I'll just double check my window here. Well, one thing I can see that I haven't, surprised that it didn't catch up to me here, but this should be decay, so it should be a negative. That constant should be negative. So help me find my negative. Where did I not put a negative in? 30 divided by that. So natural log 3/4, that probably will be a negative number. Let me just check. Okay, well, I guess it's just me being, maybe I don't have a good window. I thought I did, but let's check it again. Change the...
Can you just isolate x by algebraically?
Yeah, just do it algebraically.
Okay, if you want to see it algebraically, I'm happy to do that since I don't know what's going on with my calculator. So I'm looking for 80 to be equal to 40 e to the natural log 3/4 divided by 10. And if I then collect up some like terms here, that'll be 20 equals 40 e to the natural log 3/4 divided by 10 t. So this is 1/2 equals e to the natural log 3/4 divided by 10 times t. So that means the natural log of 1/2 equals the natural log of 3/4 divided by 10 times t. And t is going to be equal to natural log 1/2 divided by natural log 3/4. And then I'll end up multiplying by 10 since I'm got on 10, thank you. Don't know how I snuck a 4 in there. Is that quicker?
Yeah, it's quicker than a calculator.
Okay.
You have to guess the window.
Alright, I guess it's not lazy then doing that. You don't, anyways, won't argue. So this time I've got natural log of 1/2, and it's out of natural log 3/4 times 10. The moment you've all been waiting for, 24 minutes, 24.09 minutes. So by now your coffee is probably colder than 80 degrees, but at least you know that you could do it. Okay, So I think we'll tie it up here.